All right, welcome to Unit 4 on probability, random variables, and probability distributions. Pretty long unit. We're nearing the end. This is topic 4.10, Introduction to the Binomial Model. All right, first, let's go backwards for a second. How do you construct a probability distribution? Well, if the random variable is continuous, then it's actually pretty difficult. You cannot list all of the possible outcomes, so you cannot find all their probabilities. So it becomes pretty difficult. And in most cases, if the variable is continuous and I wanted you to know the mean and standard deviation, I will just give you the mean and standard deviation of X. I'll give them to you free of charge. However, if the random variable is discrete, then it is possible to make a probability distribution, but it's going to take some work. All right, first you have to decipher all of the different outcomes. You have to be able to think, use your brain and think about all the different possible outcomes that there could be for whatever X is. And then you have to use your probability skills to find the probability of each of those outcomes. And again, that's why we learned an awful lot about probability. And then once you have that probability distribution in front of you, you can use the formulas or you can use your calculator to find the mean and to find the standard deviation. So continuous is pretty easy because you can't do a whole lot, but discrete, you could easily make a list of everything that can happen if you just use your brain and find the probabilities using your skills. But I do want to talk about in this video a very special discrete random variable. And this very special discrete random variable, we can actually use a function to find the probabilities of each outcome. This special random variable is known as a binomial random variable. It is special, so it only works under a very specific situation. But if you deem that a problem is a binomial situation, then we could actually use this probability function to find each outcome that is possible. So imagine a probability function where you plug in the outcome you are looking for, and it gives you out the probability. Now, I'm not going to lie, we still need some probability skills to figure this out, but how nice is it that if we could just know the outcomes, plug the outcome in, and get the probability? That'll be pretty nice. Well, that is possible only under this brand new, very special binomial random variable. All right, so what the heck is a binomial random variable? Well, a binomial random variable, X, counts the number of successes in a given number of trials. That's really the big part. That's the big part. Given number of successes in a given number of trials. So this is like if I say to you, okay, shoot 5 free throws. And the X is how many successes you could have. Well, I could make 1 of them, 2 of them, 3 of them, 4 of them, or, sorry, I'm running into my words here, 5 of them. So that's it, right? So you're given a number of trials, and you're looking for how many successes you could have. So if I give you 20 trials, you could have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20 successes. Obviously, if I give you 40 trials, well, then you could have 0 through 40. So obviously, we try to keep it a little bit smaller here. So let's just say I had 10 trials, right? 0 successes, 1, 2, 3, 4. So this is discrete because you can list all of the different outcomes, how many successes you get in n trials. But there's a couple more rules, right? Once you understand that that is the basic part of a binomial random variable, now you have to understand there's a couple more rules. So in each trial, there can only be 2 possible outcomes. So every time you do something, there can only be success or fail. It either happens or it doesn't. So again, like making a free throw shot, you either make it or you miss it. That's a good example of this idea. Another rule is that the probability of success, which we will call P is the probability of success, must stay the same on every trial. So if I have an 85% chance of making a free throw, it's 85% on every shot. It doesn't go like a wave. It doesn't. Sometimes I get better and sometimes I get worse. No, it stays 85%. And that means that if you know that the probability of success is P, then the probability of failure is simply 1 minus P. Because remember that only 2 things can happen. It either makes the shot or it misses. So 85% chance I make it, 15% chance I miss it, but those probabilities have to stay the same. All right, each trial's outcome must be independent of the next. I mean, this is something that's really important when we talk about probability, but it's super important with binomial. So whatever happens on that first shot cannot impact the second, third, or fourth shot subsequently. And again, that kind of piggybacks with rule number 2, is that the probability of success must stay the same. It can't go up and down depending on what happened before it. And also, you must be given a set number of trials. And again, that's actually part of the definition. You must be given a set number of trials. Because if I just say you have unlimited trials, well, then you have unlimited successes. And that's not discrete. There has to be a set number. So you have to be given a certain number of trials. All right. So, I'm not going to lie to you. These binomial situations are very, very specific. So, as much as I just explained everything, it's kind of nice to go over it one more time, maybe a little slower. So if I'm analyzing a problem and I'm trying to figure out if it's a binomial random variable, first I have to ask myself, do they give you the probability of success? And can you find it? Right? So you either have to be given the probability of success, which we call P, or there must be a way that you could somehow find it. You must also be given a set number of trials and be looking for how many successes there can be within those trials. So you have to be told how many trials you have, and you have to be able to make a list of all the different successes you could have. So again, if there's 6 trials, you could have 6 successes, 5, 4, 3, 2, 1, or 0. It has to be set up that way. Now, once you determine that those 2 things are true, you know the probability of success, or you could find it. You are given a set number of trials, which we'll call N to be generic. Then you have to go and check these 3 things. 1, each trial can only have outcomes of success or failure. You cannot have 3 or 4 or 5 different possibilities for each outcome. Then, between trials, the probability of success must stay the same. It cannot fluctuate based on something that has already happened. And then thirdly, the outcome of one trial cannot impact the next. We must have trials being independent. So if all of these things are checked off, then you could officially call it a binomial random variable. Let's look at an example and make sure we understand all of these things. The probability that an adult has type O negative blood is 7%. In a group of 10 randomly selected adults, let X be how many have type O negative blood. So first, I am given the probability of success. The probability that a person has type O negative blood is 0.07. Now that also tells me the probability of failure is not having type O negative blood is 0.93. We use the word success and we use the word failure, but please do not interpret that as if you have O negative blood, you are success, and if you do not have type O negative blood, you're a failure. I don't want anybody having their feelings hurt because they have AB blood or something like that. It's just what we call it. Now, I also must be given a number of trials, and voila, I was told that there are 10 trials. Now that those things are met, I was given success, I was given my trials. Now we have to make sure that A, on any given person, they either have type O negative blood or they do not. Now, do not. That could incorporate many different blood types. A, AB, A positive, B negative, even O positive. Okay, that's great. But I'm simply identifying each person as success. You have O negative or failure. You do not. 7% versus 93%. If I look at it that way, I could check off that qualification. Second, the probability of success must stay the same. So it has to stay 7% for each person. So as long as I am randomly selecting adults, and there are millions of adults in the United States, as long as I'm randomly selecting them, it's not like taking one adult away is going to impact the probability of success. It's not like if I select a person and they have type O negative blood, that doesn't make the next person's probability change. It's the same. Everybody has a 7% chance because there's a large number of people. And lastly, what happens with one person cannot impact the next. They must be independent. And that is true because we're looking at a randomly selected adults. We're not picking out our friends or we're not picking out our family members. That's not independent. We're picking out random adults. And if I'm picking out random adults, one person's blood should not impact the next person's because it's just random. So it does appear that the initial things, success, trials, are given. And then the other three qualifications, we have independence. That does seem to make sense. I thought through that. The 7% stays the same. It's not like it goes up to 8% or down to 6%. And we also have only two things that can happen. You either have it or you don't. Success or failure. So this is a random variable that is binomial. I could actually make a list of all the outcomes. 0 people, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Sorry, I ran out of room there. But there's a list of everything that can happen. And what we are going to examine a little bit later on in this video is how to find the probabilities of each of those. But first, we have to make sure that we know how to identify that something is binomial or not. So now what I want to do is I want to take a look at a series of problems. And every one of them, we're either going to say it's binomial or it's not. And we're going to talk about why. All right, is this binomial? In a bag of 72 Skittles, 18 are red. You select 5 Skittles out of the bag without replacement. Let X be how many are red. All right, now what's the probability of getting a red Skittle? Well, 18 out of 72. What's the probability of not getting a red Skittle? It would just be the opposite of that. 1. If you're doing it mathematically, you would do 72 out of 72 minus 18 out of 72 to get the common denominator. But you get it. 1 minus the probability of success. And I was given that I'm going to look at 5 Skittles. So the first two things that are important do seem to check out. Probability of success, 18 out of 72, and then sample size is 5. All right, is it success or failure? Yes, as long as I view each Skittle as red or not red. Now the not red has a couple different colors, but again, I just looking at red or not red. 18 out of 72 versus not 18 out of 72, right? Which is fine. This is sounding good. But then we have, does the probability of success stay the same? And that's where I have a problem. The first has an 18 out of 72 chance of being red. But without replacement, the next Skittle is 17 out of 71. And then the next Skittle is 16 out of 70. That's a problem. With such a small amount of Skittles, every time I take one out that's red or not red, I'm changing the probability of what happens next. So sorry, this is not binomial for that reason. All right, here's a second situation that's going to sound a little familiar. Skittles reports that 25% of all its candies are red. You select 5 Skittles out of a large batch without replacement. Let X be how many are red. Well, once again, they gave me the probability of success, 25%. Failure is implied to be 75%. And they did tell me that we're going to look at 5 Skittles. So that is all seeming to be true. But now we got to check our other conditions. Every Skittle is either red or not red. I like that. That checks out. The probability of success must stay the same. Well, now that's true because I know that 25% are red. And I'm looking at a very large batch. And even if you take one out and it's red, you still technically have a 25% chance of the next one being red. Now, it's a large batch. So I know that we're taking one out. But even taking one out doesn't severely change the probability. It might go from 25 to 24.999999999, but it's still essentially 25% chance. So the probability of success should stay the same as long as it's a large batch. That was the problem in the previous question, is it wasn't large. It was just a small sample. So that does check out. And I should also have independence. What happens to one selection should not impact the next. It's not like in that large batch, all the red Skittles huddle together because they're all close friends. And if I grab a red one, I'm probably going to grab a red one again because they're all close to each other. Absolutely not. That should not happen. Each selection should be independent of the next. So this is a binomial situation. All right, in a study hall of 50 students, 10 have the flu. If 5 are selected at random, let Y be how many have the flu. So once again, they did tell me the probability of having the flu is 10 out of 50 kids. And that means 1 minus would be 40 out of 50 kids do not have the flu. And they did tell me that we are specifically looking at 5 students. But once again, every student either has the flu or does not. So that first thing kind of checks out. They have the flu or they do not. But the second does not. Because again, if I get a kid that has the flu, that is 10 out of 50. When I reach in a second time with this small group of students, now there's 9 out of 49 kids. And then 8 out of 48 kids. The probability changes. So once again, this is not binomial for that reason. It's also not independent because what happens on the first selection impacts what happens on the second selection. If the first selection was a kid with the flu, the second probability changes to 9 out of 49 because of that. That's a problem. All right, Maddie knows that she has 62% chance to make a free throw on any given attempt. So the probability of success is 62%. The probability of failure, 1 minus P, would be 38%. And she is going to shoot, oh, wait a minute. The question never gives me how many she's going to shoot. It says she's going to continue shooting until she makes 5 in a row. Gosh, that could take 10 shots. Well, actually, it could take 5 shots. She could make 5 in a row. That could take 6. It could take 7. It could take her 95 shots that are all misses and then until she makes 5 in a row. So the problem sounds binomial, but remember, binomial is we are given a set number of trials and we need to figure out of those trials how many can be successful. That is not what this question is asking us to find at all. It wants us to find out until she makes 5 in a row. That's not binomial. All right, Jack tosses a water bottle 15 times and records if it lands straight up or if it's on its side. No other outcome is possible. Let S be the number of times it lands straight up. So they are giving us a number of tosses. They're giving us 15 tosses, and it could either happen all 15 times, 14, 13, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, or 0 times. So that sounds binomial. The problem is, what's the probability of success? Now, they don't directly tell me, but Jake could find it, right? How do you find probability? It's the long run relative frequency. It's how many times it happens after a large number of trials. So before Jake would do his 15 tosses, he could toss it a large number of times, and through that, he could calculate the probability of success. Maybe he finds out that he has an 8% chance of this happening. The point is even though I'm not directly given the probability of success, which you do kind of need it to actually solve the problem, the point is that it is possible for Jake to figure out the probability of success. He would just have to do it a whole lot of times. So this is still binomial. Now, on every toss, it either has to land straight up or not, which is true. Those are only 2 outcomes. We do have to assume that whatever the probability is, again, let's just make up that he finds out it's 8%. We have to assume that 8% stays the same. So he can't have any hot streaks or cold streaks. So the probability of success stays the same, and that should be true. And we also have to have independence, which means what happens on one toss does not impact the next. And as long as all that is true, this can be a binomial situation. David continues to roll 2 die until he gets a sum of 7. Well, the probability of getting a sum of 7 is 6 out of 36. There are 6 outcomes out of 36 total outcomes that result in a sum of 7. 5, 2, 2, 5, 3, 4, 4, 3, 6, 1, 1, 6. There's the 6 of them. Which does reduce to 1/6. So the probability that you do not roll a sum of 7 is 5/6. But I was never told a number of trials. I need a number of trials. It just said continue to roll until he gets a sum of 7. That's not binomial. Binomial would say something like roll it 5 times, and how many times did you get a sum of 7? None? 1, 2, 3, 4, 5? So the way this question is written, not binomial. All right, Kevin will roll 2 die and get the sum of the 2 die in hopes of getting a sum of 7. He will roll the die 5 times. Oh, excuse me, misread that. He will roll the die 10 times. Let S be how many rolls have a sum of 7. Oh, this is binomial. Once again, the probability of getting a sum of 7 is 6 out of 36, which is 1/6. The opposite would be 5/6. And they did tell us 10 trials. And of those 10 trials, we could easily record never getting a sum of 7. 1 time, 2 times, 3, 4, 5, 6, 7, 8, 9. I ran out of room again. 10. There we go. And again, each toss should be independent of the next. The die's not going to remember what it did. You could only either get a sum of 7 or not. Those are the only two possibilities. Success, it happens. Failure, it does not. And the probability should stay the same. It's going to stay 6 out of 36. The sides of the tosses don't go away, anything like that. So it all should stay the same. All right. In a game involving a deck of 52 playing cards, Katie draws 7 cards out without replacement. Let X be the number of kings drawn. Okay, so let's see here. What is the probability of getting a king? Well, I hope you know there are 4 kings out of the 52 cards. The failure would be 48 out of 52, so that seems to be making sense. And it did tell us that she's going to take 7 cards. So with 7 cards, she could get 0, 1, 2 kings, 3 kings, 4 kings. Oh, but wait a minute. She can't get 5, 6, or 7 kings because there's not that many kings. So that doesn't seem to work out to be binomial. Furthermore, because she's drawing these cards without replacement, the probability of getting a king changes. For the first selection, it's 4 out of 52. If she gets a king, now she's down to 3 out of 51. If she gets a king, now she's down to 3 out of 49. Or excuse me, 3 out of 50. And then even if she does not get a king, well, then she's still down to 2 out of 49. So the probability is changing because she's not replacing the cards. Not binomial. All right, last example here. Christian knows based on previous data that 10% of her sales calls result in a sale actually being made. So Christian knows that she makes a large amount of calls over her history on the job, and 10% of those calls result in a sale. So the probability of success is 10%. Probability of failure, 90%. It does tell us that she's going to make 30 calls, and we're going to look at the number of calls that result in a sale. Now, I'm not going to do it, but it is possible to make a list of all the different outcomes. 0 sales, 1 sale, 2 sales, 3 sales, 4, 5, 6, 7, 28 sales, 29 sales, or she could make 30 out of 30 phone calls and they all get sales. Now, as long as the probability of success stays the same, 10% chance on every call, it's independent. What happens on one phone call, good or bad, success or fail, should not impact the next. That's an assumption we can make. And again, every phone call, it's either going to be a success, we made a sale, or failure, we did not. So this would be a binomial situation. So just to do one more recap, you have to be given or be able to find the probability of success. And remember, anytime you know the probability of success, you automatically know the probability of failure. So these two things come for free. And then you have to be given the number of trials, or else it's clearly not binomial. And you must be looking for how many successes we could have in those trials. So again, 7 cards, you can't have 5 kings. So that's no way that's binomial. And then once those two things are confirmed, you must consider, can you only have 2 outcomes? Yes or no? Success, fail. Does the probability stay the same on every trial? Because if it changes, that's a problem. And is each outcome independent of the next? So as long as all of these things are met, you have yourselves a binomial, discrete, random variable. All right, this is part 1 of the video for binomial. Next video is part 2, which will dive into how to actually create the model and how to find the probabilities of each outcome. Please make sure you watch it.